AP Calculus BC, Unit 5, Day 12, Lesson, Introduction to Related Rates. But really, this is a review of related rates, but we'll start with a little intro on it. So this is nothing new from Calc AB. It's going to all be the same as Calc AB. And this is the rest of Unit 5. This is what we're going to cover. So it's all review from here. So let's go over the main steps of how to do related rates problems. Oil spilled from a tanker creates a circular pond whose area is increasing 100 square inches per minute. So area is increasing. So that's a derivative of area. That's a rate change area. dAdt is increasing, which means it's going to be positive 100 square inches per minute. So units are important on these problems. Making sure you indicate if it's positive or negative. The negative usually won't be in the word, in the problem, but there will be a word that indicates it. How fast is the radius of the circle increasing? So I'm going to call that drdt. When the pond area equals 25 pi square inches. So I feel like it's good to just read through the problem and then translate it into some kind of more short expressions, summarize it. Now, drawing pictures on these is often very helpful, maybe not as much on this, but we have a circle with a center, and as the oil spills, the circle increases, and it just keeps going outwards, right? So it's going out this way. We have a radius. So usually that's one of the first things to start with after you read the problem, is start with the picture. And then you want a relationship that ties the things you know. You know something about area and you want to find something about R. Now, these are derivatives, so we don't go there yet. But we got to figure it out. Is there a relationship between A and R? So A equals pi R squared. So often it's geometric, area, volume, perimeter, things like that. After that, then we're going to want to take the derivative implicitly with respect to time. Okay, derivative implicitly with respect to time. And generally there's no time variable, so that's why it's implicit. So we're going to take the derivative of A with respect to time, dAdt equals pi is a constant, so it's going to be 2 pi r to the first power, and then you got to follow it up with the derivative of what's inside, which we assume involves time. And that's why we just write this implicitly. This is the thing that we want. We have this. We can find this. Okay, so we need this. We got to find the R, and that's where they said when the area is 25 pi square inches. So fourth step is to find other measurements that you need. And a lot of times it goes back to the original relationship you came with, A equals pi r squared. So A equals pi r squared, and we know that the area is supposed to be 25 pi. So we solve for R, square root of both sides, plus or minus. Algebraically, there's two answers. We're only going to go with the positive one, but you should show plus or minus in your work. So we have that. That's what's going to go in there. And so now we're going to plug these values in and solve for our answer. So dAdt is positive 100. I'm always very conscious about putting plus or minus. If it's positive, I'm going to put a plus to make sure I didn't forget to think about it. 2 pi, the radius is 5, and then we have drdt. Now, do we expect drdt to be positive or negative when we get done? Positive, because it's increasing. R should be getting bigger. If we don't get a positive answer, then something's wrong. So now we're going to divide by 10 pi. And we can reduce it. And so drdt equals 10 over pi. Now you need to make sure that you put the units. Most of these problems have units. This is length, radius, so it's going to be just inches to the first power over time, and this problem is minutes. And it came out positive, just like we thought it should. So those are the major steps of related rates. So you can see a big variety of geometry and algebra and things like that, though, that get involved. Here's a little more challenging one. At night, a woman 6 feet tall walks at a rate of 4 feet per second towards a street line 30 feet above the ground. What is the rate of change of the length of her shadow when she is 8 feet from the base of the light? What is the rate of change of the tip of her shadow at the same time? So, number one, we got to draw a picture, right? We got to figure out what's going on here. This one's a little more complicated. So, I'm going to draw my light and draw the ground. And then we have a woman, walking towards the light. Now, she's going this direction. So, I like to often put arrows on my pictures to show the motion of things. So, she's moving that way. And it says she's 6 feet tall, right? And she's walking at a rate of 4 feet per second towards a street lamp that's 30 feet tall all the time. That's a constant. We'll try and take advantage of that. The shadow is formed by connecting the light source with the thing that the edges that are going to create that shadow. So that's her shadow. The length of her shadow is changing. The distance between her and the street lamp is changing. Now, it does say that she's going to be 8 feet from the street lamp, but that's changing, so we can't plug that in yet. But the 30 foot's never changing. Her height's never changing. Now, it says, what is the rate of change of the length of her shadow? So we need to come up with a variable for the length of her shadow. I'm going to call it x. And so if I call the length of her shadow x, then I'm looking for dx dt. Do I expect to be getting shorter or longer, positive or negative? Well, as she gets closer, her shadow is going to get shorter, so we expect to get a negative answer. If you don't, something's wrong. Now, this rate they gave us has to be tied to something. And so this rate, how fast she's walking, affects the distance between her and the light. So when she walks 4 feet per second in 1 second, the distance between her and the light also changed by 4 feet in that 1 second. So I'm going to create a variable for this length here. I'm going to call it y. You can call it whatever you want. And so this equals dy dt. Now I got to decide, is it positive or negative? Her rate of speed, doesn't matter what direction she's walking, that it's not positive or negative. But now that I tie it to y, is y getting shorter or longer as time progresses? Shorter, so it's going to be negative. So now we kind of have all this information. Now we got to figure out a way to relate x and y together, because this is what we want. This is what we have. So we got to get some relationship between x and y without derivatives first. And in this case, there's a bunch of right triangles. In fact, there's a small one and a big one, and they're similar to each other. So number two, the relationship. What is the relationship? Well, it is similar triangles. That's a symbol for similar. And similar triangles have proportional sides. Like all their sides are proportional, meaning they maintain the same fraction. So if I say this over this equals this over this, or this over this equals this over this, you just got to, there's a lot of different ways you could set them up. So I could say 6 over x, this over this equals 30 over this. Now, not y, it's going to be x plus y would be the whole side of the triangle. So that's one way you could set it up. You could do x over 6 equals x plus y over 30, which might seem more attractive because your variables aren't stuck in the denominator. You could do 6 over 30 equals x over x plus y. There's a lot of ways we could go here. They're all going to give you the same thing in the end. Now, I personally don't want to do quotient rule. I kind of don't want to deal with these fractions, so I'm going to cross multiply 6x plus 6y equals 30x. And I do want dx dt, so we could even get x by itself. We get all the x's together. 24x equals 6y. X equals 6y over 24. X equals y over 4. Sometimes that's not reasonable or beneficial. This time it was so easy. It's like, why not? So now we're going to take the derivative implicitly with respect to time. So that's going to be dx dt equals 1/4 dy dt. And so now we're going to plug the values in and solve. I don't think we need to find anything else. In fact, all we need is dy dt, which we have. In fact, that y equals 8 feet doesn't even matter for this problem. So it's going to be 1/4 times -4. It's going to give you -1. The units are feet per second. Make sure you put the units. Now, it came out negative, which is good because that means it is shrinking, which I think makes sense, right? Like I also pointed out, it doesn't even matter how far she is from the lamp. It's always shrinking at the same amount, okay? Now, the second part of the question says, what is the rate of change of the tip of her shadow? So, I mean, we could draw another quick picture just to, it's pretty messy. The tip of her shadow, how fast is it moving? Now, that's different than how fast is the shadow changing. That has to be tied to some variable all the way here. I'm going to call it z. So we're looking for dz dt. How fast is the tip of her shadow moving? Now, I don't think it should be negative. It might come out negative if we tie it to z getting shorter. Like we do expect z to be getting shorter. But for my final answer, I don't think I'm going to include that negative. I'm just going to say she's walking towards the street line, or whatever. Tip is getting closer to the street line. Now, we can still use our x and y because we have those. And I would say z equals x plus y, which is perfect because I have dx dt and dy dt. So I'm going to do dz dt equals dx dt plus dy dt. And so dz dt, dx dt we found in the last problem was -1, and dy dt was given to us originally, which we said was -4. So dz dt equals -5. The units are feet per second. But again, I don't think we should put the negative in this answer. I'm going to put it more into words. The rate of change of the tip of her shadow, tip of her shadow is 5 feet per second towards the street lamp. It's more of like a speed, and you could indicate direction right there. Negative, if you're thinking of velocity, would be to the left usually. It's not going to the left. I mean, we could have drawn this picture so it was going to the left. I just drew the picture oriented like this, but you could have done it other ways. So it kind of makes sense that it's -5. The tip of the shadow is going faster than the shadow of her feet, or how fast she's walking. It's catching up to her. By the time she gets to the street lamp, the tip of her shadow will have caught up to her because it'll be right underneath her. So it's kind of a classic problem. Similar triangles. All right, let's do a couple more very common types of problems. So next one says, from the edge of a dock 12 feet above the surface of the water, a rowboat is being hauled in by a man at a rate of 4 feet per second. How fast is the length of the rope changing with the boat when the boat is 5 feet from the dock? At the same moment, find the rate of change in radians per second of the angle formed by the rope and the water line. Draw a picture. So, dock, 12 feet tall all the time. Rowboat being hauled in by a man at a rate of 4 feet per second. How fast is the length of the rope changing? Here's a rope. We could call R if you want. So we want to find drdt. Now, it should be negative because the rope should be getting shorter. It says when she's 5 feet from the dock. And the boat's 5 feet from the dock. Okay. There's an angle here. This is where the second part. Angle formed by the rope in the water. We're going to ignore that for a second. So we got to create some variables. We got this r. This is a right triangle, so I think we use like Pythagorean theorem. So we can call this x, we call this y, we can use a and b, or whatever letters you want, but make sure you label them on your picture. The relationship is x squared plus y squared equals r squared. Now here's the deal. Before we take the derivative, if there are any constants, plug them in now because it'll make the work easier, but they got to be constant. Okay? The height of the dock, the y value, that's constant. That's always 12 no matter what. R is not constant. X is not constant. Don't plug in 5 for X. Okay? That's going to make the work easier. The derivative is easier, everything. You're going to have to deal with it at some point. Easier to deal with it up front. Now, we need to figure out, what is this rate? Well, I'm thinking that's dx dt, right? Should be positive or negative once we assign it to x. Negative. X is getting shorter, right? And if you forgot that, you probably would get a positive dr dt, which doesn't make sense. That would mean the rope is getting longer. Should be getting shorter. So we're going to take the derivative, 2x dx dt. The derivative of 144 is 0, so it just drops out. 2r dr dt. This is what we want. We have x is 5. We have dx dt is -4. We don't have r yet. So r is the hypotenuse. So to find r, we're going to use this relationship again and plug in 5 and plug in 12 and figure out what r is at that moment. So it's going to be 25 plus 144. So it's going to be 169. Square to both sides, plus or minus. We just want the positive one this time. So that's what's going to go in there. So we get -40 equals 26 dr dt. We divide both sides by 26. And so dr dt equals -20 over 13. And the units for radius for the rope should just be one-dimensional. It's going to be feet, and time is seconds. And it came out negative like we expected it to. That's good. Now, if you hadn't plugged in the 12 earlier, you would have had an extra 2y dy dt in your work, and then you'd have to say, well, dy dt is 0, and eventually it would drop out. It's just easier to put those constants in earlier so they drop out right away and the work is not as messy. Now for theta, we got to figure out how to relate theta to r, x, or y. I personally am going to try and stick with using x and dx dt and not try and rely on anything new. Because 1, what if I didn't need to find that? 2, what if I found it correctly and it's just ugly? 3, what if I found it and I got it wrong? I like to rely on the original information as much as possible. So I think I'm going to want to use x and y. So which trig function involves opposite and adjacent? Tangent. Now you could do sine equals opposite over hypotenuse. You could do cosine equals adjacent over hypotenuse. Those would work. But I just feel like you're opening yourself up to harder work, more work, uglier work. So we got to take derivative. Now remember y is 12, so let's go and put that in there. In fact, I'm going to rewrite this because I don't want to do quotient rule. I'm going to say this is 12x to the -1. That's going to be a super easy power rule now. Derivative tangent is secant squared d theta dt, which is what we're looking for. -12x to the -2 dx dt. I mean, you could have done quotient rule if you want. So this is -12 over x squared dx dt. Secant is 1 over cosine squared, right? And cosine is adjacent over hypotenuse, but it's in the denominator, so we're going to flip it. So the hypotenuse is, at the moment we're looking to evaluate it, R is, I think we found it somewhere, right? What was R? R was 13. So it's going to be 13 over, well, yeah, hypotenuse is, the adjacent side is 5 squared. X is 5 squared. Dx dt is -4. Now the d theta dt, do we expect it to be positive or negative? Is the angle getting bigger or smaller as the boat comes in? The angle is getting bigger. So we should get a positive answer. D theta dt equals, so this is going to be positive 48 over 25 times 25 over 169. So d theta dt equals 48 over 169. The units are radians per second, and it came out positive like we expected it to. So little trig got involved there. So there's lots of ways to relate these things. We've seen somewhat triangles, we've seen area, we've seen Pythagorean theorem, we've seen basic trig. Now, cone problems are very common, and cone problems have some issues and some ways to make the work a lot easier. Liquid is being cleared of sediment by pouring it through a cone-shaped filter. If the height of the cone is 16 inches, the radius of the cone at its base is 4 inches, and the liquid is flowing out of the cone at its tip by 2 cubic inches per minute, then how fast is the height of the remaining liquid in the cone changing when the cone is half full by volume? Let's draw a picture. So it's an upside down cone that's filtering. There's a certain level of water at some point that has a radius. Now the radius at the top is 4 inches, and the height at the top is 16. And there's a height inside that's changing, and we want to know how fast is the height changing. So we're looking for dh dt. Should come out negative because the height should be shrinking because we're losing water at the tip. Now this is a volume of water, so this is dv dt, and it says 2 cubic inches per minute. Now, should we treat it negative or positive? Well, since we're losing it, we're going to put a negative on it. Okay. So we want to find this when it is half full by volume, which is not when h equals 8. So we need a relationship. Volume of a cone is 1/3 pi r squared h. Now, right now, if we take the derivative, dv dt, we're going to have to do a product rule, 1/3 pi r squared times dh dt plus h times 2/3 pi r dr dt. And it's pretty messy. And maybe sometimes we have to do that. But this time, we can avoid it. We can get everything in terms of r or h before we even start with the calculus. And I recommend that. So the tip here is to get v in terms of all h or all r right away. What we're going to use to do this is something we're going to have to use no matter what. So this time, do we want all r or all h? Well, it depends on what they give you and what you're looking for. Since we're looking for dh dt and they don't tell us anything about radius, we want all h this time. Now, if they ask us for dr dt, we'd want all r. Now, how do we get in terms of all r, all h? Well, what happens here is that we have similar triangles. See the similar triangles, the 2 right triangles? So we can do the sides are proportional. We can say r over h equals 4 over 16. And so then if we want all h, we're going to solve for r in terms of h. So we need 1/4 h, and we're going to plug that into the radius so that we get all h's. So let's do that. Volume equals 1/3 pi. The radius is 1/4 h. It all gets squared, including the 1/4. So we get pi over 48 h cubed. This is the volume formula we want to use before we start introducing the calculus, because you see that ugly derivative we did? Well, the derivative this time is going to be pi over 16 h squared dh dt. Done. So much cleaner and easier. And guess what? To get dr dt and r, you would have to use this relationship anyways, eventually. So let's just do it right away, okay? Now, we're looking for this. We have this. The one thing left to find is the h, and it is not h. If it said half full by height, h would equal 8. So what is h when it's half full by volume? Well, we got to find the full volume. So the full volume is 1/3. We could use our new formula, by the way. So I'm going to do pi over 48. The full height is 16 cubed, right? And so if we want half of that, I'm going to multiply by half. So what's the height there? I'm not going to multiply all these numbers out yet because I think that would actually create more work in the end. So we have 48, we have 1/2, pi over 48, 16 cubed, I'm going to write 16 times 16, equals pi over 48 h cubed. And we got to find h. So the pi and 48 cancel each other out. So that works out nice. We have to take the cube root of both sides, no plus or minus. So h equals 16 over the cube root of 2, right? Cube root of 16 times 16 times 16 is 16. We could rationalize the denominator, be cube root of 4 top and bottom. So I give you 16 cube root of 4 over 2, which would become 8 cube root of 4. So this is sort of the nicest height for the half full by volume. So we can plug that in now. So we have dVdt is -2. We have the height is 8 cube root of 4 squared dh dt. So now we just got to try and clean this up. So -2 equals pi over 16. This is going to be 64 cube root of 16. And so that reduces that to give you 4. And then we could take the cube root of 8 out. So that gives you another 2. So now we're at 8 pi cube root 2. So we're going to divide both sides by that. So dh dt equals, if we don't rationalize the denominator, it'd be 1 over 4 pi cube root of 2. And the units would be inches per minute. We could rationalize the top and bottom, so multiply by the cube root of 4. And that would give you negative cube root of 4 over 8 pi inches per minute. So that's another possible answer. So cones can be a little tricky, but there's some things. That's by far the easiest way to do that problem. So, but hopefully this jogged your memory a bit. And we're going to do a couple assignments practicing this to make sure we're good at this again. But that was a quick little redo of related rates, and now we just got to practice it.